When we study engineering systems, it's going to be helpful to know what we think of as a system. So many courses in engineering study problems or they study technologies. So what's different about when we study a system? In this video, I want to take you through the characteristics that make an engineering system a system. This isn't an exhaustive list, but this is a pretty useful list to get us started with thinking about what's different when we study systems compared to when we study problems or when we study technologies. And the first of these is that we have to have boundaries. This might seem obvious, but let's explore this first characteristic of a system. An essential characteristic is it has to have a boundary. Inside that boundary, there can be lots of different things happening in our system, and that's fine. But if we are unable to define some criteria by which we understand what's in and what's outside the boundary, then we don't really have a system that we can study. Fuzzy boundaries won't do. One of the courses that many engineers take is thermodynamics, and thermodynamics is really good at formalizing what the boundary of the thermodynamic system is. Often that will take the name of a control volume. And anything that passes in or out across this boundary is an exchange between the thermodynamic system and what's sometimes called the system environment. This idea of a boundary is really important in both technological systems and biological systems. For example, a cell has boundaries, and in the case of a cell, it's the cell membrane through which material or energy can pass. So this idea of a boundary is not unique to technological systems, but it's essential to understand the criteria and what's in and what's out. In the case of the cell, it could be a physical boundary made up by this complex protein membrane, but it could also be a boundary based upon some other criterion. It doesn't have to be physical. It could be an informational boundary, or it could be some other definition, as long as we're able to distinguish between those things that are inside the system and those things that are outside. The things that are outside are typically called the environment, and sometimes when conditions in the boundary of the system are fixed, we call those boundary conditions. They can be fixed, they can be flexible, but we know where they exist, both mathematically, in space, or in information. The other thing about systems that are really important is that they have components. The components themselves might have their own boundaries, but it's the interaction between the components that are inside the system boundary that is really important. So these components cannot be separate from one another. When we're interested in systems, it's not just a random collection of things that don't have any relationship to one another. A system knows what's in, knows that it has different components, and the important thing about the components is that they interact. The state of one component depends upon the state of other components. It's that kind of interaction that makes the system so interesting, that gives us the system's perspective. So you can imagine this in plan view when we're looking at this hypothetical abstract system. But another way to look at these components and their interactions is as if we took a cross-section through this abstract system. And in this cross-section, we're looking at some of these interactions in a different way. The system exists at a higher scale than any of the individual components. We could examine just this one component and understand its operations and all its little subsystems, but when we examine the system as a whole, we must look at all of these components. And that's what I mean by this abstract cross-sectional metaphor. We have to look at how the components work together, how they interact. we're looking at them at an aggregated scale rather than the individual scale. And this is one of the interesting things about systems. Ordinarily, the way Newtonian physics asks us to look at or understand a phenomenon is to take it apart and find its atomic root cause. What's the smallest, most reduced element that we need to understand before we fit all the system, or we fit all those elements together? Those would be the components. It could be an atom. It could be a proton or an electron at some of its most fundamental chemical units. But when I say we want to work at a higher scale, it means not that we want to take things apart. The systems view asks that we look at them as a collection, that we put them back together. So when we go down, that could be reductionist, taking things apart to examine the individual components and understand how the components work, thinking that the phenomena inside is a function of those components. But the systems view pushes against that. The systems view is integrative and asks, what kinds of phenomena do we observe when we take this higher scale of observation where the components interact? They may work together or in opposition. So far, we have three things: the boundaries, the components, and the interactions. And those three things exist both in science and in engineering. But in engineering, there's a fourth thing that is very important. A system must have a purpose, and that's because engineering is a design discipline. Science is a descriptive discipline. It's meant to describe the way the world works, and often to build mathematical models of the world that highlight those features we're most interested in and allow us to make predictions about the way the world works and then test those predictions in experiment. But engineering is a prescriptive discipline. Engineering says what should be, not what is, but what's the world that we want to live in. Engineering might count all the raindrops and add them up and say, this is where we should have a river. Where science stops with the counting and the describing, engineering remakes the world in the interests or in the image of the design. It is the engineer's job to conform the world to their imagination, which is why engineering is the bridge between science and fiction. It's the engineer that uses the descriptions of science and the creative imagination of the way the world could be, merges them in the middle to create the artifacts of design. So engineering systems must have a purpose. That's our four things: the boundaries, the components, the interactions, and the purpose that characterize our study of engineering systems. In a future video, I'll talk about complicated systems versus complex systems. The distinction turns out to be pretty important.